Part 2, Exponential Growth and Decay. Exponential growth or decay. Suppose a substance grows or decays exponentially as a function of a variable t that represents time, and the amount at time t is a of t. Then a of t equals a sub 0 e to the kt, or we could say a naught, a sub 0 or a naught, is the initial amount of the substance. K is the relative or exponential growth or decay rate. So if K is positive, then the amount is growing exponentially. And if K is negative, the amount of our substance is decaying exponentially. So what is the half-life of a substance? A half-life is how long it takes until half of the substance has decayed. So the half-life of a radioactive substance, the time required for half of the substance to decay. Let's try some problems. The population of the world in 2017 was 7.577 billion, and the relative growth rate was estimated at 2% per year. Assuming the world population follows an exponential growth model, like the equation we just looked at, find the projected world population in the current year. So our equation again is a of t equals the initial value times e to the kt. So in this case, our initial value is going to be 7.577, and our k value is 2% or 0.02. So this is what our equation looks like. Now it's asking what's the projected world population in the current year. So this currently is 2025 when I'm recording this video. So 2025 is 8 years after 2017. So a of 8 equals 7.577 e to the 0.02 times 8. Put that in the calculator and I get 8.892 billion people. So according to this model, the population in 2025 should have been 8.892 billion. Now I just looked up the actual population. This is in June of 2025, and the population today is 8.231 billion. So quite a bit lower than the 8.892 billion. But if we think about that, a lot has happened since 2017. We had a pandemic, we've had a lot of social unrest, a lot of political unrest. That all affects growth rates of our population. So a lot of things have happened. So it makes sense that our population would not be the same as the projected population. Let's try another example. Here we have a population of bacteria that is growing according to the equation A equals 1700 e to the 0.12 t, where t is in minutes this time. What is the initial population? So the initial population is this value right here. So that is the initial population. At the beginning, at time 0, there are 1700 bacteria. Now let's estimate the number of minutes it will take for the population to exceed 3985. So we'll take this equation. We want the amount after however many minutes to be 3985. We start with 1700. And we want to find t. So I'll start by dividing by 1700. So 3985 over 1700 equals e to the 0.12 t. Change this to logarithmic form. And you could simplify this fraction, but we're going to put it in the calculator anyway, so I'm not going to bother. And then we need to divide by 0.12 to get t by itself. So I have the natural log of 3985 over 1700, close parentheses, then divided by 0.12. Don't forget to close your parentheses on what you're taking the log of, or your calculator will not give you the correct answer. And in this case, the correct answer is about 7.1 minutes. The population of Salt Lake City in the year 2000 was 181,779, so 181,779 people. In 2010, it was 187,082 people. If we assume the population is following this exponential growth model, what would be the expected population in 2030? So this is going to take a little bit more work. We need to find our k value first. So our initial value is 181,779, and the amount after 10 years, so from 2000 to 2010, is 187,082. So to write everything here, I have 187,082 equals the initial value, e to the kt, in this case k is 10. And we can use this to find what k is. So we need to find that k value, that growth rate. We don't have that right now, but I have enough information I can figure that out. So I'm going to divide both sides by the 181,779 equals e to the 10k. Then put it in logarithmic form. So I have the natural log of 187,082 over 181,779 equals 10k. Then I can divide by 10. And this will give me that growth rate. So k is approximately equal to 0.00288. Now I'm just going to keep that value in my calculator for a little bit. I don't want to round too much, so I'm going to use the whole value, not the rounded value. Now I need to actually answer the question. So what would be the expected population of Salt Lake in 2030? A of 30, that's 30 years after 2000, would be the amount, the initial value, times e to the kt. And this would be 30 years after we started. And I know what k is. I didn't write it there because I'm going to use the value that I saved in my calculator. So in my calculator, I will type 181,779 times e to the 30 times previous answer, whatever that value is stored in your calculator. And it should be about 198,157. So 198,157 people. An unknown radioactive element decays into a non-radioactive substances. In 860 days, the radioactivity of the sample decreases by 29%. So if it decreased by 29%, then there is 71% left. Okay, so what is the half-life? We know that after 860 days, there was 71% remaining. So if we started with 100% or 1, we ended with 71% or 0.71, we have e to the k times 860. And this will tell us what k is. Once we find k, then we can find the half-life, but I don't know what k is yet, so I'm going to find that first. So I'm going to put this in logarithmic form, and I have the natural log of 0.71 equals 860k. Divide by 860. So k is the natural log of 0.71 divided by 860, which is approximately negative 0.000398. And again, that's rounded. I'm going to keep that value in my calculator so I don't have to use a rounded value to answer the question. Now the question is, what is the half-life? So how long until 50% is remaining? I know what k is, so if I put this in logarithmic form, I have the natural log of 0.5 equals kt, and now I'll divide by k. So in my calculator, I'll put the natural log of 0.5 divided by previous answer, and I should get approximately 1740.5 days. So our half-life about 1740.5 days. Now let's answer question B. So this was part A. Part B, how long will it take for a sample of 100 milligrams to decay to 87 milligrams? So 87 equals 100 times e to the kt. I know what k is. If you want to get that value back in your calculator, you can put back in your calculator the natural log of 0.17 divided by 860 so that value is stored in your calculator. Here I divide both sides by 100, I get 0.87 equals e to the kt. Put this in logarithmic form and divide by k. So the same steps as what we did to find the half-life. And we get 349.69 days.